Here we're looking at a concept in chemistry that we refer to as equilibrium, okay? And the best way of thinking about equilibrium is, as the word suggests, as a kind of balance. And this is a really tricky concept. And there are three things that you need to be aware of that affect equilibrium. So let's just go through sort of some of those concepts and the idea. So there are three conditions that you need to be aware of: concentration, pressure, and temperature. And the way to think about it, and this is a gentleman tightrope walking across the Niagara Falls, which did actually happen. If all of a sudden something starts going down on this side, the man is going to lower this side of the rod to sort of balance out his equilibrium position to get balance again. And that's what happens in chemistry. As one thing changes, the opposite has to also happen in order to sort of counteract that effect. So if the concentration goes up, then that's going to create more of the thing that is less concentrated, right? So we'll go through these three different conditions, and we're going to use a reaction called the Haber process or Haber process, and this is the reaction that goes on here. Now, the important thing to note is that you have an arrow going in both directions. Unlike a conventional reaction where you just have an arrow going in one direction, you will get a symbol that, and it normally looks a little bit more like that, that shows that the reaction is going in both directions. Now, what that means is that both of these reactions are going on at the same time, right? So as these two combine to make ammonia, this is actually breaking apart to form these two. So this is constantly going back and forth. And when we think about equilibrium position, we're thinking about if this is 100% nitrogen and hydrogen, and this is 100% ammonia over here, somewhere along this axis is my equilibrium position. All right, so if I was, let's say, here, I would have 50% nitrogen and hydrogen and 50% ammonia. Over here, it would all be ammonia. Over here, it would all be nitrogen and hydrogen. And this position here that we're talking about is what we call the equilibrium position. Now, in this case, this is the product that we want. So we want this position as far over here as possible, right? So how do we do that? Well, there are three things. So the first one, concentration. So just so I rub this out, if you think about concentration, if I increase the concentration of one of these sides, right? If I increase the concentration of, let's say, nitrogen and hydrogen, that means there is more nitrogen and hydrogen to react, and as a result, the equilibrium position will shift over here. Okay, so it will move to the right, or it will favor the products, or it will move in the forward reaction or favor the forward reaction. So that's the language you use. You're not going to create 100% ammonia, you're just going to get more ammonia because you're counteracting the increased concentration of nitrogen and hydrogen, because these two are then going to start colliding and reacting more often. Okay, so that's the first one. That one's quite straightforward. The second one is this idea of pressure. Now, all three of these are gases, right? So all three of these are gases. And I've got 1, 2, 3, 4 molecules of gas on the left and 2 molecules of gas on the right. Now, if I have a box like this, and I've got 1, 2, 3, 4 molecules, and then I make that box smaller, well, actually, those 4 molecules are now closer together. Right? It's not a particularly difficult concept to understand. When I make the box smaller, the gas particles are close together. That increases the pressure. It's what you do with a tyre. You put the gas particles closer together to make the pressure in the tyre higher. And therefore it can inflate and keep a whole car up. Now, as a result, what these will do is these will try to counteract that higher pressure. And as a result, they will react together, because on the right hand side you've only got 2 particles of gas, and as a result the equilibrium position will move to the right hand side and it will favour the ammonia. The last one is temperature. And temperature is a tricky one because temperature, the concept is sort of an A-level concept to understand. However, to get the direction, you don't need to have the A-level. So the forward reaction is what we'd call an exothermic reaction, and the backwards reaction is called an endothermic reaction. In an exam, you'll get told which way is which. If I decrease the temperature, we have to counteract that with the hotter reaction, so the reaction that releases energy, and that is the exothermic reaction. So a decrease in temperature will shift to the hotter reaction. So a decrease in the temperature will shift to the hotter reaction in a very simplistic way of thinking. So lower temperature favors the exothermic direction, hotter temperature favors the endothermic, colder temperature favors the exothermic. So it's the opposite. So colder favors exo, hotter favors endothermic. All right. Now, something to bear in mind in this particular process, what's happening is we want as much of this as possible. Now, therefore, you would think that your conditions would be a high concentration on the left, high concentration of this, good. I would want high pressure as well because I've got less gas particles on the right, so that would favour the right hand side. And I would want, because it's an exothermic reaction, I would want a low temperature. All right, and that's what you would probably consider. So this is stuff that goes up to grades sort of 7, 8, 9. These are the conditions that you reckon you'd imagine would favour this. High concentration of these will shift the equilibrium position over here. High pressure will shift the equilibrium position to the fewer gas particles, and low temperature will favour the exothermic. And the equilibrium position will be right over here, which is true. However, because of the low temperature, and this does occasionally come up, because you've got a low temperature, that means that the particles haven't got the energy to collide and react, and the rate of reaction is slow. So actually they use quite a high temperature, but not too high. So we don't use a really high temperature because otherwise it will shift the equilibrium position right over here. But we do need to use a high temperature so that enough particles can pass the activation energy so we have an increased rate of reaction.